Okay, can you? We're on Jamboard, right? All right. Your teacher is always prepared. Your teacher wants you to do really well in your test and all your evaluations. So, last time we we left off looking at circuits, and we're gonna go back and review it a bit. But now we're not gonna focus on power plants. That's actually a bit more complicated than we think. So we're going to go back to the ones that you studied in grade 9, which is a basic circuit. So what are the components of a basic circuit?
A switch.
Actually, the switch is a complicated circuit, you know?
Okay, then the power source.
Yeah, so let's bring it back to the basic needs. So we need a power source. Now, a power source is just a cell. So whenever you see the symbol written this way, this is called a cell. And a collection of cells is called a battery. Ah, good job, good job. Now, there's a convention that you need to follow to distinguish which is the positive terminal and the negative terminal. So the positive end from the negative end. So the long line or the short line. So which one represents positive? Which one represents the negative terminal?
Long positive.
Say it again.
Long is positive.
How did you remember that?
Yes, I think how I picture this is like two ends of the battery.
Which way?
Like the short one is like one side of the battery where there's like the little like bulge up, and then the long one is just the bottom of the battery. You see, I'll draw it for you.
You know, I thought I was very clever, but maybe you're more clever. You think of a different way.
What slide are we on?
Oh, slide 12.
You see that, Mr. Morales?
So the part that comes out of the battery, that's the negative side or positive?
Negative.
You know, I never remember that, so that's not the best way to remember this. You're really smart.
I'm pretty sure it's positive though.
No, Josephine, it's negative.
It's negative, Josephine.
Okay, so now you're going to hear your physics teacher's very clever way of remembering it. To make a plus sign, you need more material than a negative sign. So that's why the longer one is longer because it needs more material to make the positive sign.
So we should be negative because it takes less effort.
Oh, the battery is. So Max is wrong.
Oh yeah, I did say positive.
So misinformation.
He's spreading fake news.
Oh,
No, I said positive.
Censorship.
Okay, so see now you're gonna remember my way because my way is more clever. So the longer one requires more material to make into plus sign. That's why that's gonna be the positive end, and the other one will be the negative end. And Chow, she helped us out last time because she looked at electricity as moving electrons, and if the electrons are moving, we call that the electron flow. So that is what is actually really happening, but because we're people of conventions and we like to be more conservative, we're going to follow the conventions. So instead of the electrons moving, we're going to consider the protons are moving. And the direction...
But to clarify, it really is the electrons that are moving, right?
Yeah, 100%.
And really the electricity is coming out the negative side.
Yes.
Oh yeah, I did say negative.
But then for electricity, we're going to consider that the protons are moving. So we're going to call this conventional current. And the symbol that we used last time is we use the capital letter I. You could use the lowercase I, but that's not commonly used. So capital letter I, and conventional current just measures the amount of charge that passes through a cross-sectional area in a given time period. So again, the basic circuit is we need first a power source, then we identify the positive end, the negative end. But as Oscar was saying, the power source is really important because what is the power source providing?
Where's the power source? What?
So the power source provides the power, but that's not a very good way of thinking it. Now let's think more in terms of physics. So think about energy. The power source is what gives the potential energy, and that potential energy gets used as it travels along the wire into electricity. So we need a power source. But a more technical way of saying that is we need an electric potential difference. Now, sorry, I'm going to erase this a bit, otherwise it's going to get too messy.
Censorship.
All right, but electric potential difference is a mouthful to say, so normally no one ever says electric potential difference. Instead, we say, what do we say?
EPD.
Not even that, we just say electric potential. Right, think about potential energy. We never said gravitational potential energy, we just said potential energy, which was now misleading because now this is also potential energy. So to distinguish it, we say electric potential. All right, but electric potential is not quite the same thing as electric potential energy. This is the voltage, so the change in voltage. Actually, this is one of the most confusing parts in electricity. Remember I told you about the electric potential? So electric potential energy that one we use delta EE. And what's the relationship between the two? Q is charge. And actually that is the connection between the two, right? So electric potential energy is the amount of energy that a charge has when it moves through an electric potential difference. So again, electric potential energy is the amount of energy that a charge has when it moves through an electric potential difference. So if we think about a battery provides a potential difference. So when you have a charge going through a potential difference, it's going to gain electric potential energy, which it then uses to move around the circuit. Any question on that part? Because again, I know it's confusing, so make sure you ask your questions.
Wait, can you say that again?
Can you put like numbers into this? Like say if a battery has 5 watts or whatever, then this will have like how many volts or whatever, like just so we can understand it.
Okay. What's the most common battery voltage?
I don't know, you should know.
No. You guys seen it in your batteries, like for your control remotes, things like that?
1.5? I don't know.
1.5, that's usually 9 volt or 12 volt
9
batteries.
volts.
So let's say we have a 12 volt battery, but that just tells you the potential difference. And let's say that we have a charge of, let's say the most basic charge is going to be 1 coulomb per second. So how much energy does this charge have when it moves through the battery? So how much energy is gained in 1 coulomb per second moving in a 12-volt battery? It's a simple calculation. You should be able to just use mental math right there. Oh, sorry, I put the wrong unit. Sorry, coulomb.
I don't even know how.
Yeah, sorry. For charge, it should be just coulomb. Yeah, sorry. So if we have 1 coulomb of charge moving in a 12-volt battery, how much energy does it gain?
One.
Let's look at it.
I don't know. Can you write out the math?
Well, the formula is the electrical energy of a charge is going to be the charge that moves through an electric potential difference. So what is the electric potential difference? 12 volts. And what is the charge moving through this 12 voltage?
1 coulomb.
So how much energy does it have?
12.
12 joules. And if you have 2 coulombs of charge moving through this battery, how much energy do they have?
Wow.
At least 2. At least 2 joules.
No, 24 is going to be...
I said at least.
Okay, fine. So you see, the battery is a potential difference. So it's like it has this potential difference between the two terminals. So when the charges are moving past it, they get charged up with more energy. And the amount of energy that they gain depends on how much charge is going through that potential difference. So if 1 coulomb goes through 12 voltage, it gains 12 joules. If 2 coulombs goes through 12 voltage, it gains 24 joules.
So electric potential energy is your Q value times voltage?
Yeah, so the voltage, why it's useful, is kind of like convention. So that way, it doesn't tell you how much energy the charges have. It just tells you, hey, if a charge goes through here of 12 voltage, then you have to determine how many charges are moving to determine the actual energy that you're going to have to work with. So that's why like the voltage is like a standard. So like, oh, you have 12 volt batteries, 9 volt batteries, 1.5 volt batteries, and then it depends on how you connect them that you could have different energy. So if you have a 1.5 volt battery and you have 1 coulomb of charge, how much energy does it gain when it goes through this battery?
1.5.
1.5 joules. So voltage is kind of like the standard to think about the charges going through, and then you determine how much energy they have when they go through this formula.
So I increase the coulomb.
That we're going to talk about that. So far, does this make sense though?
Yes.
Okay, so to have a simple circuit set up, we need a power source and we need a closed circuit, a closed wire. But what has to be specific about this wire? What are some of the properties that we want in the wire itself?
Low resistance?
Conductible.
Actually, that's correct. Ideally, we want a wire with low resistance. But what are some of the chemical properties that we look for? So Chow said the electrons are moving. So for electrons to be moving, should they be held together very tightly or should they be loosely held around the nucleus?
Tightly.
Which one?
Wait.
Tightly held to the nucleus or loosely held around the nucleus?
Loosely.
Right, because if you want things to be moving, then you don't want those things to be tightly held in one particular place. So one property of the wire that needs to be true is that the electrons in the nucleus, they need to be away from the nucleus, so they need to be loosely held. So whenever you give them some potential difference, then they're going to move. So what property of material is that called? Think about plastics versus metals.
Conductivity.
Conductivity, right? So you need a conductor. So what's the property of conductors? They have loosely held electrons. And this is usually true in metals. Right, because what is moving in a current?
Electrons.
Electrons. So see, what is really happening, our electrons are moving. But of course, then we get messed up into thinking that protons are moving when they're not, and it's messy, right?
Yep.
Okay, let's go to slide 14. We're almost finished. So I think Oscar's gonna get this for sure right away. Okay, so we have the same battery and we're using the same conductor, so the same wire, maybe copper. But the only thing that we're changing now is we're making the length of the wire shorter and shorter in each scenario. So now we want to identify a trend. As length of wire decreases, what's going to be happening to our circuit? What will be increasing? Now, here's a bit of a joke. Why do people say that they want to avoid having a short circuit? What happens in a short circuit?
Combust.
Because it's shorter, the resistance is still the same, but because it's shorter, it gets hotter.
And eventually, if it's too short, what's going to happen to the wire itself?
It's gonna melt.
Yeah, like so Max said combust. I don't know if that'd be the right word, but melt. Combustion. No, because combustion you need reaction with oxygen, right?
That's hard.
So I think it melts. Melts would be more appropriate to say.
I
And
didn't know you were suddenly an English major.
I'm not. I'm a minor.
I thought that's chemistry, no?
Oh, I'm a chemistry teacher too, you know.
Ah, that's congratulations.
Yeah, that was really hard. I'm better at chemistry than physics, actually.
So why are you teaching
Bruh.
physics?
Because it's harder to find physics teachers than chemistry teachers.
So you get paid more, right?
Mm-hmm. You got to follow the money. So in this case, you already figured it out. You're so smart. We have that as we decrease the length of the wire, because we still have the same amount of charges moving about, and those charges have the same energy that they gain at the battery. So there's a new law that we're going to study. All the energy that was gained in the battery has to be lost by the time it comes back at the other terminal. So all the energy needs to be used up.
It does?
Yeah.
But technically, is the energy not going back in the battery?
No.
Besides the one that's lost to thermal energy?
No. So this is one of the laws. So all the energy that the charges gain at the power source needs to be used up by the time they come back to the power source.
Oh, so it heats up the wire more when it's shorted because no matter what, it has to be used.
Yes, now you understand it. So that means that because we decrease the length of the wire, but the energy still needs to be used up, it has less space to spread it out. So when you concentrate that energy in a small area, it's going to increase in temperature, it will get too hot, and then melt.
So no matter what, it has to be used up.
Yeah, this is a law.
Wait, did you say a joke yet?
Pardon me?
You said you had a joke, right?
Yeah, because it's short circuit. Short circuit is when it melts, but not a lot of people know that. And I knew Oscar would know it, so and he proved me right.
Oh, that was funny. I just forgot to laugh.
That was a joke?
No, it was Max, but it was really funny. I forgot to laugh.
Okay,
Yeah, because from that expression, that makes you understand physics so much. You're like, oh, a short circuit is when it melts. So if it melts and it, your brain just blows up because of all the connections that you just made.
Okay.
Right? Okay, so we're almost finished. So in this case, what do we say? All the energy needs to be used up as it travels along in a complete circuit. And because we are decreasing the length, then the energy needs to still be spread out, but that energy is going to go into thermal, which means it's going to heat up. And if it's too short, it causes a short circuit, which means that the wire melts.
But if we add something like a light bulb to the circuit, the wire isn't going to get as hot, right? Because more of the energy is used for the light bulb instead of into resistance, yes?
Yes. So if we look at the light bulb, the light bulb is just a wire that's exposed. So what happens to this little short wire? It's going to heat up. But when metals are heated up, they tend to glow. So the glowing is just due to the same factor that we said. The energy needs to be used, and it is getting used up in this small section of the wire. But what's so special about the wire is that it doesn't melt at certain currents. So that's why when you were doing those labs when you were younger, they always said, hey, make sure that you look at the light bulb, because if you put certain light bulbs in certain conditions, it's going to burnt up because it's too much for it. Do you remember that?
Yeah.
I remember it in Mandarin, so yeah.
Yeah, so that's why in physics we always have to order a lot of light bulbs, because students don't really listen because you're so used to at home plugging things wherever you can, and then you don't care, especially you got so much money. You like
So
whatever.
if it weren't for MTO, will we be doing a light bulb lab?
No, a little bit more. We'll be doing magnetic labs.
Huh?
Are you kidding me? We missed that?
Mm.
Okay, next year when I'm TNT, I'm coming back to your class and come see you, right?
But I might be teaching chemistry because Yekwe wants to put me back there. All right, so for conclusion, we saw that all the energy needs to be used up in a closed circuit, and because of that, as we decrease the length of the wire tends to heat up. By heating up means that it's going to increase in thermal energy. And if the wire is so short, it causes a short circuit. And in a short circuit, all that means is that the wire length is too short, that it melts the wire.
Resistance is also exponential, right? Like the hotter it gets, the more resistance there is.
We're going to talk about resistance on Monday. That's going to be our next topic. So right now, I just wanted to introduce this idea that no matter what, in a closed circuit, all the energy needs to be used up. So that's a law. Now, the person's name that wrote this law is really hard to pronounce. So we're going to get to that on Monday. We're going to practice saying his name.
Law has no exception.
Okay, everyone. Have a good weekend. Thank you for listening in. And then I'll see you on Monday.
Okay.
Goodbye.
Thank you.
Bye-bye.
Bye-bye.
Thank you. Bye.